Hello, my name is Muhammad Ushaidi from Group 1 that we're gonna do about project Gearbox Inline Shaft. So my task that was assigned to me is S1 to the 1. So the abstract that I do for this project, we want to design and perform a compact planetary inline gearbox with 5:1 ratio delivering 265.78 Newton meter torque at 10 kilowatt with optimized the standard. The rarity and innovation that we want to achieve is 12% weight reduction through carrier optimization, follow FMEA guided program. So the introduction overview I do is we want to design a planetary inline gearbox for industrial conveyor. The application is the industrial conveyor with 10 power kilowatt, and also with the shaft position we're gonna do is inline. So the key challenge for this to achieve and the objective we want to achieve is the balance compactness, durability, and load distribution for continuous operation. The problem statement we have here, the conventional spur helical gearbox faces is space efficiency and uneven wear, limited torque density for 10 kilowatt application. So the practices we do is planetary design, improve torque density, compactness, and load sharing. So here are the example of what the project we want to do. Planetary gear in inline shaft. The literature review overview is industry requirement is gearbox must balance durability, efficiency, and compactness. The planetary gear outperforms per helical for high torque density. The key standard we follow is ADMA and ISO guideline for the gear tooth, load capacity, thermal limit. And the emerging trend that we can see is here IoT monitoring, advanced material for noise weight reduction. The methodology, the part I do is the overview systematic design approach and 5 key phases. Number 1, system composition. Number 2, concept evaluation. 3, embodiment design. 4, detail design. And lastly, optimization. And the system composition divide to 3 key subsystems: power transmission, structural support, and auxiliary system. So for the chapter 4, the result is which I do in the bearing, I do in Katia. The calculation came from DD, which is calculate for the bore size, and I do the part in Katia. So this is our bearing that we want to achieve for the inline shaft gearbox. And conclusion for my part is from S1, in comparison to spur helical alternative for layer application, the planetary inline reduction gearbox demonstrates more superior torque density, and it can balance the load distribution by effectively converting the objective 10 kW at 1.00 RPM to 360 RPM, which follow the 5:1 ratio. And my recommendation for this is in future version, IoT sensor should be added to measure temperature and vibration in real time. And this will allow for more accurate repair planning to extend and can extend the gearbox useful life even more. So thank you.
Hi, I'm Arif Iskandar and I was in charge for Chapter 2 Literature View, a crucial part of our Gearbox design project. In this chapter, I explored real engineering patterns and design references that directly shaped our CATIA model, from the gear arrangement to the material selection. I made sure our design followed key standards like AGMA for strength, ISO for bearing life, and also ASME for structure safety. I also analyzed safety, environmental, and performance factors, ensuring our gearbox isn't just functional, but durable, efficient, and ready for industrial use. This chapter laid the technical foundation for the entire design. I'm proud that my work helped ensure our gearbox meets real-world engineering standards and delivers high performance.
Hi everyone, my name is Muhammad Ikhwan Daniel. For the methodology part, we follow a 5-phase process starting from system decomposition, followed by concept selection, embodiment, detail design, and finally the optimization. In the system decomposition phase, the gearbox was broken into 3 main parts: the power unit, structural unit, and auxiliary system. The main requirement was to transmit 10 kilowatts at 1800 RPM with a 5:1 split ratio reduction. For concept selection, we chose the planetary inline gearbox due to its compact design, high torque to weight ratio, and smooth operation. And also in the embodiment and detail design, we model all our components in CATIA. Finally, in our optimization phase, we reduce the carrier weight by 12%, and we upgrade the material for better fatigue resistance and enlarge the shaft to reduce deflection.
Good afternoon. Hi, my name is Manjuman. So for the last part, which is presentation, today I would like to present my part, which is why we use inline Linux gearbox. We choose this because it is with its compact size, high torque capacity, and also it is efficient load distribution. So we have used fixed string of gear with 8 teeth and also 32 bore for bearing and also shaft design. For stress analysis, we calculated using torque of 260, and also for bending moment, we use 100 Newton torque, and the shaft pass 50 checks under bond micro stress. I also did my part to identify the key failure risks, and also while I use manual calculation, I recommending using 3D finite element analysis for better accuracy in future. Finally, I involved in planetary gear and shaft construction in Katia. That's all.
Hi, I am Miru Amri, and I was responsible for the S5 section, which focuses on the scope, performance measurement, and design optimization of our planetary gearbox. I began by defining the project scope, which limits our design to mechanical components only using standard materials and AGME or ASME standards. For performance evaluation, I focus on torque output, efficiency, and structural stress using AGMA equations and Lewis gear formula. In the design optimization stage, I implemented changes like carrier lightning pockets, shaft oversizing, and material upgrades to reduce weight and improve strength. All my major products and parts were modeled in CATIA with iterative update based on performance results. And that is all from me. Thank you.